4.1 is all about exponential functions. So an exponential function would be where you have b, some value b raised to the x. So your exponent is the variable. B is going to be your base. And x is your variable that is an exponent. B is going to be a positive constant. And x has to be a real number. Okay, so here's some examples. So we could have f of x equals 2 raised to the x. We'd have g of x equals 10 raised to the x. H of x, which is 3x plus 1, 3 raised to the x plus 1. And we could also have j of x, 1/2 raised to the x minus 1. Okay, so something that is not exponential would be h of x equals -1 raised to the x. That is not going to be exponential because it's a negative base. So remember how I said positive constant here? So this is negative, so that's why. And then another example would be, well, the reason this doesn't work is let's say we have to the half, and we have 1 to the half power, negative I to the half power, which really means the square root of -1. Because whenever you take something to the half, you actually square root. When you square root a -1, you get an imaginary number. So that's why that is not exponential. Okay, we can evaluate exponential functions by substituting it in a number for x. So if we look at our notes, let's look at number 1. So evaluate exponential functions just means that we are going to substitute in a value for x and solve. So this first one gives us an exponential function that models the average amount spent in dollars at a shopping mall after 8 hours. What is the average amount spent to the nearest dollar after 3 hours? So we have our function, substitute in 3 for x, and then solve. So let's look at ours that we're supposed to solve. Here's our exponential function. It models the population of India, f of x in millions. X after 1974. Find India's population to the nearest million in the year 2028. So since x is represented by years after 1974, do y'all know how we could find out what we're going to use for x? Yeah, subtract them. So we'll do 2028 minus 1974 to figure out what our value of x that we're going to use. 54. Yeah, 54. because this tells us X years after 1974. So that's why you have to do that. So this is going to be our X value that we're going to substitute in. So we would do F of 54 equals 574 times 1.026 raised to the 54, to the power of 54. And we can use the calculator to do that. So whenever you put it in, let's see if I have mine. 2,295 million. Because it says f of x in millions, so that's why we have to put million on there. 2,295 million. Okay, the next set of problems will deal with graphing exponential functions. So the best way to graph them is by making a table of values. We can do this by hand. We can do it with the calculator, but you need to look and see what is the pattern that it is following. So if we have x, and then we have f of x, which is y, we'll start out with 0. So let's say x is 0 for f of x equals 4 raised to the x power. You do 4 raised to the 0 equals 1, because anything raised to the 0 power is 1. And then we do 1, 4 to the first power, it's 4. 2, 4 squared, 16. 3, 4 raised to the third power. So the pattern is you're multiplying by 4 times the previous. This is called a geometric sequence. So what is 4 to the third power? 64. So exponential growth means it is growing at a exponential rate. Kind of like whenever coronavirus first hit, they were doing predictions and they were doing all of the reports of the number of cases. Did y'all see how it went like that? Whenever it started out, it just exploded. It wasn't linear. It wasn't quadratic. It started out kind of low and then it just exploded up. So that this is what exponential functions look like. So if you were to put it in the calculator, let's put it in the calculator. So it's a sharp increase. So it goes 1, 4, then 16, and 64, and then you'd multiply times 4 again. And see how it never goes below the x-axis? So that gets us to the next thing on in our notes, which is the characteristics of exponential functions. F of x equals b raised to the x. So the first characteristic deals with your domain and range. So domain is your x, so it's going to go from negative infinity. It's all real numbers. Negative infinity to positive infinity. In range, you're always going to do x to the 0 power first, which always equals 1. And then it's not going to cross your x-axis like that other one. So it's not going to go below 0. So y is going to be greater than 0. And we can write that as 0 to infinity. Second thing will be our x-intercept. It won't have one. It will never cross it or touch it, so there is none. So if b is greater than 1, then it's going to be increasing. Like that. But we have been talking about this being a positive constant, right? So we are not going into it can be between 0. So if it's between 0 and 1, it's going to be decreasing. So it's going to go down like that, but never cross the x-axis. So an example of that, so let's look at our graph, and let's do 0.5 raised to the x, or half raised to the x, and let's see what that looks like. So it is a decreasing function, but it never crosses the x-axis. It still has the same domain and range. X-intercept none, and then it follows the between 0 and 1 being decreasing. Okay. So let's look at more of these graphs. So we already did just a quick sketch because we looked at it in our calculator of how it looks. We're not going to worry about that. 2b, we have 1/3 raised to the x. So if you were to plug them in and look at the table, you would see that it is a decreasing function because the b is between 0 and 1. So it is decreasing. But then on this other one, 3/2 is 1/2. So it's going to be increasing. It's going to start out at 1, and then it's going to go up. So let's look at what that looks like. So let's put in 1.5 raised to the x power. And graph it. So how does this one compare to the other one, the 2x? 2 raised to the x power. Do I remember what the other one looks like? Or was it 4? What did we do? Okay, it was 4. So 4 raised to the x. How do they compare to each other? The 4b would be steeper. So it's going to go more like that compared to the other one, which was a sharp increase. So I'm just going to write here less steep than f of x equals 4 raised to the x. Okay, let's look at the next one. Use the graph f of x equals 2 raised to the x to obtain the graph g of x equals 2x plus 1. So we do have some transformations. This is on page 468, how the exponential function changes. So it is this horizontal translation. So anytime you add some kind of constant to your exponent or subtract it, you're going to shift it horizontally. So this would be, if it's plus c, it would shift left c units. If it's minus c, it'd shift right. So it's the opposite. So horizontal, whenever you do plus or minus, it shifts it left or right, in the opposite of what you would think. And then if you were to add or subtract to the exponent, to the b of x, then you're going to shift it up or down. And then we have reflections, and then stretches, vertical stretch and horizontal stretch. So those are our transformations. So if you want to look back at that or take a picture of this, it's also on the e-text that's on the My Math Lab. Okay, so when we have f of x equals 2 raised to the x, and then we have g of x 2x plus 1, that means it's going to be shifted. It's a horizontal shift. Left 1 unit. And then 2D, we have 2 raised to the x, and then 2 raised to the x, and then minus 1. That's like changing your y-intercept. So this is going to be a vertical shift down 1 unit. Okay, objective 3, evaluate functions with base e. So the exponential function that's given models the percentage of high school seniors who applied to more than 3 colleges X years after 1980. What percent of high school seniors applied to more than 3 colleges in 2013? Okay, so E. Do y'all remember anything about E? The natural log? Y'all learned about it in pre-cal? Not yet? Okay. So the natural base E is 2.7. So we can use E. We do E raised to the first power, 2.7182. So where E comes from is, I'll just show you this. You don't have to write this down. That we have 1 plus 1 over n raised to the n power. So whenever we plug in numbers and we want to get the biggest number possible for n, as you get n closer and closer to infinity, your natural base e will go closer and closer to the actual value, which is 2.72. So e to the x is called your natural exponential function. In calculus, you're going to see as n approaches infinity, 1 plus 1 over n raised to the n is going to approach e. So you'll see that later on in calculus. Okay, and then we just have a few problems of just application. So we can go ahead and solve this problem dealing with the exponential function with the base e. What do we need to do? What are we going to plug in for x? Do what? Yeah, 33. So x is going to be 33 because you would subtract 2013 and 1980 to get what x is. Then you plug that in. So g of 33 equals 32.7. E 0.02172 times 33. There we go. So whenever you do that, you get 66.9. And it says what percentage, so we're just going to round it. So 67%. So approximately, whenever you plug it in. Do y'all know where the E is on your calculator? Okay, let me show you where it's at. It is down here by the LN, which is dealing with logs. So we have log, we have LN, and we have E. So you would put in, I don't know, what is the problem? 32.7, and then E, and then you'd plug in the number 0.0217 times 33, which would be 66.9. Okay, and the last two problems deal with compound interest formulas. So this is the formula for compounding interest, depending on if you're doing quarterly or monthly. So the sum, a sum of 10,000 is invested at an annual rate of 8%. Find the balance in the account after 5 years, subject to quarterly compounding. So since it's quarterly, how many times would that be per year? 4. So we would say n equals 4. So we will use this formula when you're dealing with compound interest. And then you'll use on 4B this formula whenever you're talking about continuous compounding. So you have simple interest, and then you have compound interest. And then compounding is how often it's compounded. And this one's continuous. And T is time in years, or yeah. And R is your rate. P is principal amount. So on this next one, we have 10,000 invested at an annual rate of 5.5%. Find the balance after 5 years, and it's subject to monthly compounding. So if it's monthly, how many times in 1 year will it be compounded? 12. And time would be 5 years. The rate on this one is 5.5%, but you would change it to a decimal. So 0.055. And then your principal is 10,000. So once you know each one of your variables, then you can plug it into the formula. So it'd be principal 1 plus the rate over 12, and then 12 times 5. So make sure you can plug that in and get the answer that's down the bottom, which is $13,157.04. And then whenever you do continuous compounding, use the A equals P principal, and then E, right, times time. E is that natural base with base E. So that'd be 10,000. E, and then rate would be 0.055. And then time is 5. I'll post the assignment up next period. And then tomorrow we'll do 4.2, 4.3, and then a review and a test this week.